This is material on energy balances with closed systems. So what we're going to do with this is solve these problems is we're going to carefully read the problem statement. We're going to evaluate which terms in the energy balance are zero, and then we'll write a simplified equation taking out all unnecessary terms, and then plug in known values and solve for the desired unknown. Okay, so this is our energy balance right here. This is a change in potential energy. Potential energy is going to be changes in either the potential or kinetic at the molecular level, okay, like changes in pressure, changes in temperature. And then we have also kinetic, a change in energy that's kinetic, a change in energy that's potential, and then we have heat that's added to the system, and then work done by the system. Now, one of the things that we'll notice is that this is either positive or negative, depending on which textbook or source you get it from. But if it's anything that's going to cause, let's say all of these others are zero, for example, if it's going to cause the internal energy to increase, then you'd have a negative work, okay? But this is work done by the system as defined here. Okay, so let's just go over this first example. We have a gas cylinder, okay, and this gas cylinder contains nitrogen at 200 atmospheres and 80 degrees Celsius. As a result of the cooling at night, the pressure in the cylinder drops to 190 atmospheres and the temperature to 30 degrees Celsius. So which of the terms in the energy equation are zero? Okay, so we're going to have, let's just go ahead and write this out again. If we recall, this is our energy balance right here for the closed systems. Okay, and for this gas cylinder, we are going to have no kinetic energy. The gas cylinder isn't moving. The gas cylinder didn't change elevation. But we had some heat taken out of the system, but no work was done by the gas either. So we just have these two terms left over. Okay, so those other three are going to be zero, and then for the non-zero terms, are their values positive or negative? Okay, so let's just go back to this again. So it cooled down, so heat was taken out of the system, so that's going to be negative. And for this to hold, then the internal energy also had to drop. Okay, so both of those should be negative values. Okay, let's go on to the next example. We have water that's pumped from one reservoir to another that is 300 feet away. The water level in the second reservoir is 40 feet above the water level of the first reservoir. How much work per mass of the water was performed? So let's just ask this question first. What is the system? It's going to be the reservoirs and the pump. Okay, so it would be all of this. We could just put a big box around this or circle around this. Okay, and then is this an open or closed system? Okay, so open or closed. If no mass is leaving or entering this system, then we're going to say that it is a closed system. Okay, so let's just continue with this example. Same problem statement here. Water, we're pumping it up 40 feet. It's 300 feet away. Actually, that information is irrelevant. Okay, only this information right here is relevant. Okay, so here's our energy balance right here for the closed system. So which terms are zero? Okay, so if we say that, make some assumptions here about these reservoirs. Okay, pump it up to a higher reservoir up here. If the kinetic energy is zero, so the lake water isn't swirling or moving after the transfer, then we're going to say that the kinetic energy is zero. The potential energy, though, on the other hand, that changed because we went ahead and raised the elevation of the fluid. And let's say we didn't heat or cool the water, then that is going to be zero. And let's say the temperature or did not change of the liquid, so the internal energy stays the same. So all we have are these two. Okay, so the pump is going to do the work to and this is work done by the system, so that's going to be negative work by the pump on the system, and then the potential energy is going to increase. Okay, so which terms are zero? We're going to have delta U, kinetic energy, and Q are going to be zero. And then what is the simplified form of the energy balance? Okay, so all we have is that delta energy potential and then the work done by the pump. And that is going to be the delta energy of potential, okay, is always is for fluids, or is going to be mass times gravity times height. If you remember, energy is going to be force times distance. Okay, so this is the force due to gravity, and then exerted over a distance, so we had a change in height. If we did have some kinetic energy change, that would be 1/2 mv squared, where v is the velocity of our fluid, mass is m, and then times 1/2. Okay, but we don't have any kinetic energy change here. We just have a change in height. Okay, so what was the work performed? How was it performed? It was performed by the pump. And then what is the answer? Okay, so let's go ahead and just rearrange this equation. Okay, right here. Okay, now we want the work per pound. Okay, so we can divide both sides by m here, and that gives us this equation right here. Okay, so that's going to be our change in height is delta H, and then G is the gravitational constant, W is the work, and then M is the mass. Okay, so if we just plug in that for water, okay, so this is our gravitational constant G, there's our delta H, and then we can't forget the conversion, okay, from pound mass to pound force. We have to use this conversion factor here to convert those. And okay, so that, and then a conversion factor for BTU from foot-pound force. Okay, and then that gives us 0.33 BTU per pound mass. Okay, so let's just go on to, and then just in different units right there. Okay, so how much energy is needed to raise the level in the upper reservoir by 1 foot? Okay, if the surface area is 8 square miles. Okay, so 8 square miles for this reservoir. We want to raise it by 1 foot. Okay, so let's just go ahead and calculate the mass of water that needed to be moved just for a 1 foot change in the reservoir, and so that is going to be 1.4 times 10 to the 10th pound mass. Okay, so a whole lot of mass that's moved. And then if we look at the work, then that's going to be, we use this from what we had calculated before, and then multiplied by our mass, and then we have that many kilowatt hours. Okay, so if kilowatt hours are about 8.5 cents per kilowatt hour, then it's going to cost us about $114,000 to move that water up. So if your swimming pool is 8 square miles and you need to pump it up from 40 feet, it's going to cost you a little bit of money to fill up your swimming pool. However, that would be quite a large swimming pool. Okay, and this also assumes 100% pump efficiency. We know that's not going to be the case, so it's actually going to, you need to divide it by your efficiency and then get your new cost with less than 100% efficiency. Okay, so let's say we just let the water flow downhill and there's no turbine or anything like that here. We just let it flow downhill. Where does the energy go? Okay, so like rivers that flow downstream, where does all that energy go? Well, when it's flowing downstream. So friction, it's actually friction that causes a slight increase in the water temperature, delta U. And so if we knew that it was 0.33 BTU per pound mass, and then we can see that that's going to raise the temperature by about 1/3 of a degree Fahrenheit. Okay, so if we drop 40 feet, that energy that went into pumping it uphill, if we don't recover it going down, it's just going to raise the temperature of the water by a little bit. Okay, and that was a change in the internal energy, or delta U. Okay, so just a couple terms on these energy systems. When we say isothermal, that just means constant temperature. Okay, and so just, you have a system, and then after a little bit of time, a new state of your system, it just means that the temperature is equal. Okay, and Q may not be zero. We may be adding or removing heat, but that's okay. We can have something like an exothermic reaction, but cooling to maintain the temperature constant. Okay, now another term is adiabatic as well. Now adiabatic actually does mean Q equals 0. So no heat is transferred through that boundary that we had described. Okay, so for the reservoirs, we put our boundary around here, so no heat is transferred to or from the system. Okay, so it's like well insulated, for example. Okay, so now we're going to go on to just a couple example problems just to work through these. Okay, so I'm going to switch over here, and let's just go ahead and do this problem. Okay, so air is at 300 degrees Celsius and 130 kilopascals, and it flows through a horizontal 7 centimeter. Okay, let me draw that just a little bit better here. Okay, so this is a 7 centimeter internal diameter pipe at a velocity of 42 meters per second. Okay, so first of all, we want to go ahead and calculate the energy per time, assuming ideal gas behavior. Okay, so how much energy did it could we potentially recover if we have an 100% efficient turbine, from this this flowing fluid? Okay, so so what we want to do is first of all just write our energy equation, our kinetic energy equation, and that's going to be 1/2 mv squared. Okay, so that's actually m dot v squared, so you have to use a mass flow rate versus just a mass there. Okay, so what do we know in this? We can calculate the mass. Okay, so let's just go ahead and calculate this m dot, and that is let's see, that's going to be rho times the area times the velocity. Okay, and that's going to be equal to our mass flow rate. Okay, and then our density. Okay, let's just continue down here. Our density is going to be the pressure over R, gas constant, times temperature, times the molecular weight of air. Okay, so we have all that information here. It's 130 times 10 to the third pascals times 29 grams per mole. That's for air. Okay, and then I'm going to put 8.314 pascals meters cubed per gram mole Kelvin. All right, and then I'm at 573 Kelvin. So you need to make sure this is in absolute, so I had to add 273 to that. Okay, so that's going to give me, for density, that's going to give me 791 grams per meter cubed. Okay, so I can go ahead and calculate, plug this back in here. I can also get my area. My area is just going to be pi d squared divided by 4. And then I have my velocity as well. So when I calculate all of that out, my m dot is going to be 128 grams per second. Okay, now I'm just going to go ahead and plug this back into the equation up above, and also my velocity. And so I'm going to get my kinetic energy is going to be 1/2 and then times 128 grams per second times 42 meters per second, and then square that, and then just as a unit conversion, a kilogram per 1,000 grams. Okay, so that is going to be 113 kilogram meters squared second squared, and that is going to be 113 watts or joules per second. Okay, so that is the kinetic energy of this stream. Okay, so now let's go on to B. If we instead used 400 degrees Celsius air instead of 300 degrees Celsius air, how much more kinetic energy are we going to have? Okay, now this is just the kinetic energy, not of the molecules, but of the flowing gas. Okay, so it's not going to be the molecules which influences the internal energy, but so for part B, we're going to have air, and how much? Okay, so we're going to do m dot is going to be constant. Okay, just because we changed the temperature, that does not influence the mass flow rate. Okay, and and then we also had the air. Let's just say the air coming in. Okay, and that's going to be 300 degrees Celsius. We have a heater here, and then we have 400 degrees Celsius coming out. Okay, but our density changes. Okay, density equals 130 times 10 to the 3 pascals, and then times our 29 divided by 8.314 times 673 now, and that's going to be 674 grams per meter cubed. Okay, so less dense. Before is 791, now it's 674, and then we have a new velocity, okay, which is going to be m dot over v rho a, and that's going to be equal to 49.3 meters per second. Okay, so before we had a velocity of 42, and now we have a velocity of 49.3 because we had to heat up the gas. So let's just look at our delta kinetic energy. That's going to be 1/2 m dot times V2, V2 minus V1 squared. Okay, so that's going to be our change in kinetic energy, and that is equal to, when we work out all the math, that's 42.6 joules per second, or watts. Okay, so that's how much more pumping energy we needed to put into it to get it up to that velocity. It was going to be an additional 42.6 watts. So in part C, it asks a very interesting question. Why would it be incorrect to say that the rate of transfer of heat to the gas in part B must equal the rate of change of kinetic energy? Okay, so we can't say that because we had another term there in our energy balance, and that was going to be equal to, okay, so we're just considering these two, but we also need to consider the delta change of internal energy. Okay, so we can't neglect that term. This is due to a pressure increase or decrease, or a temperature increase or decrease, for example. That's going to change the kinetic or potential energies of the molecules themselves. Okay, whereas these refer to the heat added to the system or the work done by the system. Okay, so let's just go on to just one more example here. Suppose you pour a gallon of water on a yowling cat 10 feet below your bedroom window. Okay, how much potential energy does the water lose? Okay, so annoying cat, you have a bucket of water and it's 10 feet below your window, and you pour water on this poor cat. Okay, so let's just go ahead and start with our energy balance here. Delta U plus delta kinetic energy plus delta potential energy equals Q minus W. Okay, so we're not going to change the pressure temperature of our fluid. We're not going to heat it up before we pour it onto the cat. We're not driving a turbine or something like that, generating energy as that water flows downhill. So we just have the change in kinetic energy plus a change in potential energy is going to be equal to 0. Okay, so if we just look at the potential energy that was lost by dumping this water, that's going to be mg and delta h. Now remember, this is our force times a distance, and so that is the delta energy. And then also our mass is going to be the volume times the density. Okay, so that for 1 gallon, that is going to be 1 gallon of volume times 1 foot cubed per 7.4805 gallons. Okay, and then times 62.43 pound mass per foot cubed. Okay, and then that equals a gallon of water is about 8.346 pounds mass. Okay, so that's how much mass of water we're pouring on that cat. And then if we go back and plug that in, this mass here, and calculate our delta potential energy, that is going to be 8.314 pound mass. Okay, times 32.2 foot per second squared. Now we got to put our conversion in here as well to convert from pound mass to pound force. Okay, and that's going to be foot second squared. Okay, so those are going to cancel out on the pound mass, and then we had negative 10 feet. Okay, so our change in energy then, that was going to be 83.46 foot-pound force. Okay, and I'll put the negative there. Okay, now we know in this that that's also going to be equal to the rise in kinetic energy. Okay, so the velocity of the water as it drops. Okay, so that is going to be equal to 1/2 m times v2 squared minus v1 squared. Okay, let's say it's just initially at rest. Okay, so we start to drop it, and then it's going to accelerate, and so therefore that's going to equal 83.46 foot-pound force, and that's going to equal 1/2 mv2 squared. Okay, and then if we just solve for v2, then we can calculate the velocity. Okay, and if I rearrange and take the square root, then that is just going to be 2 times 83.46. Okay, foot-pound force. Okay, divided by 8.346 pound mass, and 32.2 pound mass, pound force, foot per second squared. Okay, so velocity 2, that's going to come down at 25.4 feet per second. Okay, so that's the velocity at which it hits the cat. Okay, so true or false now. And then energy must be conserved. Therefore, the kinetic energy of the water before impact must equal the kinetic energy of the cat after impact. Okay, so maybe the cat will be moving at 25.4 feet per second right after the impact, but that statement is actually false. Okay, and one of the things to note on this is that our delta U, okay, is going to change as well. Okay, so it's going to heat up that water a little bit, just like we saw from the reservoir problem. From dropping it, some of that energy may transfer to the cat as it starts to run away. Okay, so just to review what we covered today. Okay, so we covered application of closed energy systems and wrote an energy balance, and then we went through a couple examples such as the gas cylinder and the reservoir, and then went through a couple others as well, dealing with the gas bottle, and then dropping this onto this water onto a cat.